Good morning, champs. Today we extend the Cauchy integral formula to multiple poles. The main idea is this. One big curve around several poles can be replaced by a sum of small curves, where each small curve surrounds exactly one pole. So the integral over the big curve becomes the sum of the integrals over the small curves. Now, consider the integral of e to the z divided by z times z minus 1 cubed over the circle centered at 1/2 with radius 3/2. First, we identify the poles. The denominator is z times z minus 1 cubed. So we have a pole at z equals 0 and a pole at z equals 1. The big circle contains both of these poles. So instead of trying to apply Cauchy directly, we split the integral into two parts. One small circle goes around 0, the other small circle goes around 1. We choose radius 1/3 for both small circles. Why 1/3? The distance between 0 and 1 is 1. So if we choose a radius smaller than 1/2, each circle only contains one pole. 1/3 is just a simple, safe choice. Now, the original integral becomes the sum of two integrals. First, the integral around 0. Around 0, we rewrite the function as something divided by z. The remaining function is e to the z divided by z minus 1 cubed. Now we apply the basic Cauchy formula. We evaluate the remaining function at 0. That gives minus 1. So the first contribution is minus 2 pi I. Now the second integral is around 1. Around 1, we rewrite the function as something divided by z minus 1 cubed. The remaining function is e to the z divided by z. Since the denominator has power 3, we use the higher order Cauchy formula. Power 3 means k equals 2. So we take the second derivative of the remaining function and evaluate it at 1. This gives e. So the second contribution is pi I times e. Finally, we add both contributions. Minus 2 pi I plus pi I e. So the final result is pi I times e minus 2. The key idea is simple. Each pole contributes its own term, and the total integral is the sum of all contributions.